Bismillahirrahmanirrahim. A'udhu billahi minash shaitanir rajim. Bismillahirrahmanirrahim. This is my lecture about the course of thermodynamics, having the course code of PHY331. The title of today's lecture is Thermodynamic Equilibrium and Equation of State. In today's lecture, I will cover basically the thermodynamic equilibrium. Thermodynamic equilibrium actually the combination of mechanical equilibrium, chemical equilibrium, and thermal equilibrium. So we need to develop the concept of all these three type of combination of all these three type of equilibriums. Furthermore, the next part of the lectures is devoted to the understanding of equation of state. So in thermodynamic equilibrium, first we need to know some of the basic concepts relevant to the thermodynamic equilibrium, and we need to know and define the thermodynamic systems. So a body or matter that is under consideration and that is confined in space by walls which separate it from the surrounding is called as a thermodynamic system. It might be a gas that is enclosed in a cylinder. The gas is confined, so this is some sort of a thermodynamic systems, and the surrounding is defined as the boundary that is in touch with the thermodynamic system by diathermal, adiabatic, or some other sort of walls is called as the surrounding of that systems. So the system under consideration is the thermodynamic system. So how we can describe the thermodynamic system? There are some parameters or variables that are actually called as the coordinates of the thermodynamic system. These are actually the macroscopic description in which you measure some of the macroscopic properties, measurable properties, just like the pressure, temperature, and volume of the gas. So change of a state in the microscopic parameters, if we change the properties of the systems, the microscopic properties of the system, the thermodynamics of the system is changed. So the thermodynamic system may interact with the systems by the exchange of heat, mechanical ways, exchange of particles, or by the exchange of some chemical reactions. So if you consider that a system is separated from the surrounding by diathermal wall, or maybe by an adiabatic walls, by an adiabatic wall in which it cannot interact with the surroundings, chemical interactions, mechanical interaction, or thermal interaction with the surrounding. So this system is called as isolated system. In thermodynamic system, we are not basically interested in the isolated system, although we are interested in the system that is interacting with the surrounding, because in that particular system maybe the energy is converted into work, or maybe some other sort of internal energy. So we are basically interested in a system that can interact with its surroundings. So we can move further to understand the thermodynamic equilibrium. But before understanding the thermodynamic equilibrium, we need to know the mechanical equilibrium. In case of mechanical equilibrium, if there is no unbalanced force or torque in the interior, or also none between the system and surrounding, so this is called as a mechanical equilibrium. If the system is not exchanging particle with its surrounding, say for example if you consider a gas cylinder in which it is open, there is no piston on the gas, and the gas is present in the vessel, and there is no piston on it. So this means it can mechanically interact with the system. The gas particle can come and it can go out. So this is a type of mechanical interaction. So if there is no if we consider that there is no mechanical interaction, or another side we can say that there is no mechanical equilibrium, there is no exchange of particle between the system and the surrounding. So we say that the system is in mechanical equilibrium. And the other type of equilibrium is the chemical equilibrium. Means if there is no chemical reaction taking place in the systems, and the chemical composition of the systems is same throughout these systems. I mean, and it does not vary with the passage at time. So we say this system is in chemical equilibrium. In some cases, we have endothermic or exothermic reaction, in which chemical reaction occurs, in which the heat is produced or it is absorbed, and the chemical reaction is going on. So this is not considered to be a chemical equilibrium when there is no more any chemical reaction taking place in the system, and the system is stable with respect to the chemical reaction. So it's called as a chemical equilibrium. And the third one is the thermal equilibrium. So in thermal equilibrium, if the system is not exchanging heat with the surrounding, so it means if the temperature of the system and the surrounding, I mean, we are not talking about the isolated system, we are talking about the system that is in contact with the surrounding. So if it is not exchanging, there is no net heat flow in a specific direction, so we say that the system is in thermal equilibrium with the surroundings. So in that case, the temperature of both the system and the surrounding will become same. This thermal equilibrium can be easily explained by the below example. Here we have two systems. One is system A and B. This is system A and this is system B. The temperature of system A is 100 degrees centigrade and the temperature of system B is 20 degrees centigrade. When these two systems are brought in thermal contact with each other, then due to the gradient, the heat will flow. I mean, the heat will flow from an object or from a system that is represented as a having a high temperature to a system represented as B having lowering temperature. So the consequences will be that the temperature of system A will be decreases and the temperature of system B will be increases, and this increase and decrease in temperature will be continue until both the bodies achieve the same temperature. And here you can see in the next stage, if we consider system C and D, I mean, in this case both the systems achieve the same temperatures. Both the systems achieve the same temperature when, I mean, both system C has a temperature of 50 degrees centigrade and system D has a temperature of 50 degrees centigrade. There is no net heat flow in some specific direction. Of course, it's exchanging heat, but there is no net heat flow in a specific direction, and that is why we can say that system C and D are in thermal equilibrium with each other, while system A and B are not in thermal equilibrium with each other because they have different temperatures. And in this case, again I want to remind that all the systems, I mean, are not isolated with each other, not isolated from each other. They are connected with each other by diathermal walls. So this is a sort of the thermal equilibrium and the explanation of thermal equilibrium. We can further explain the thermal equilibrium. Two system A and B are present and they are enclosed by a boundary that is actually an insulating boundary. There is a thermal insulation. The whole system is separated from the surrounding by an adiabatic wall. So it means it cannot exchange heat with the heat and energy, or maybe mechanical particles, the particle with the surrounding. Though the system A and B having different temperatures, they are present inside and they are connected with each other by diathermal walls. I mean, within the system, within the interior of this boundary, the system A and B can interact with each other. So in this case, if system A has higher temperature than system B, I mean, the temperature of system A is represented by TA and the temperature of system B is represented by TB. If we consider that system A has higher temperature than system B and they are brought in thermal contact with each other, so what will be the result? The result will be that the heat will flow. I mean, depending on the heat will flow, and the heat flow depends upon the difference of temperature. If there is huge difference of temperature, there will be huge flow, and if there is slow difference of temperature, I mean, the heat flow will be slow. But anyhow, the heat will flow from the body having higher temperature to a body having lower temperature, and this heat flow will continue until both the bodies achieve the same temperature. Keep in mind, again, both the systems are separated from the surrounding by by an adiabatic wall, that is called as a thermal, and that is actually the thermal insulation. So this is a little bit more understanding about the thermal equilibrium. We can move forward and try to understand the thermodynamic equilibrium. So thermodynamic equilibrium is actually the combination of thermal equilibrium, chemical equilibrium, and mechanical equilibrium. If there is a system which is at the same time in thermal equilibrium, chemical equilibrium, and mechanical equilibrium, then we can say that this system is in case of thermodynamic equilibrium. So it's actually the thermodynamic equilibrium is a combination of thermal, chemical, and mechanical equilibrium. So all these equilibrium states should be achieved at the same time. So this is something about thermodynamic, and in that case we can easily measure the properties or the macroscopic parameters of the system. So if we consider a system that is in thermodynamic equilibrium, so there is no tendency in this change in the change of the state of the system if it is not connected with other systems. I mean if it is insulated from the surrounding. So state of the thermodynamic equilibrium can be described in terms of macroscopic parameters that not involve the time, and it could be explained by in terms of the thermodynamic coordinates. And the thermodynamic coordinate could be easily measured when the system is in thermodynamic equilibrium. But if we consider a system to be in non-thermodynamic equilibrium states, non-equilibrium states, then we cannot exactly measure the properties of the system, the thermodynamic or the macroscopic property of the system, because it's changing with time. I mean, if it is changing with time, I mean that if we measure its property, maybe after some time it will get, or it will achieve a new value. So it means we cannot measure. I mean, of course we can measure, but that is not a particular case in which we can describe the property of the system, because it might not be correct, because so normally the macroscopic properties are measured when the system is in thermodynamic equilibrium. In non-thermodynamic equilibrium case, the properties are not measured. It is measurable, but is not authentic. So we can go or move toward the next part of the lecture, that is actually the equation of state. We develop the equation of state for any particular systems, any particular thermodynamic systems. And as I told you before, a thermodynamic system may be a gas or a mass of gas that is enclosed in a cylinder, that is a closed system. So there are some measurable properties. I mean, that is actually the macroscopic properties of the system, that is the pressure, volume, and temperature of the system. It could be easily measured. So the equation of state actually defines the relationship between these measurable macroscopic properties of any particular systems. It says that if we fix some of the properties, I mean maybe two of the properties among the pressure, volume, and temperature, then the third one is I mean we cannot control the third one. It will have some value that is defined by the nature. So if we consider an example in which we fix the volume at a particular point and then assume some arbitrary value to the temperature, then we shall not be able to vary the pressure at all. I mean the third property we cannot control. And similarly, if we choose volume and temperature, then the value of P at equilibrium is determined by nature. So that means if we consider any of the two property to be measurable property, or we can measure it, the third value can be determined by the nature. And the third one case is that if P and T are chosen arbitrarily, then the value of phi is not fixed at equilibrium. So this is the third case. So actually if we summarize all the discussion about the equation of state, the general concept, the general description is that if we fix or we determine the value of two of the macroscopic parameters of a thermodynamic systems at thermodynamic equilibrium positions, then the third value should be determined by nature, or we cannot control all the three values at the same time. We can only control the two values simultaneously. So among the three variables we have that is actually P, V and T. Only two are independent variables and the third one is actually a dependent variable. This is the summary of all this discussion. So if we express the same thing in terms of equation, so that is called as an equation of state. So the next slide will show us the equation of state. Here this is the an equation of state for a system of gas that is at low pressure, and that is for an ideal gas. It's actually called as PVNRT. P is the pressure, V is the volume again, R is and T is the temperature. R is a constant quantity that is called as a molar constant, and N is the number of moles. The above equation can be further generalized to a next form that is called as P small v is equal to RT. Here the V, that is actually the small v, that is called as the molar volume, and the molar volume is actually the volume V per mole. So this means is more specific. So this is the other form of the ideal gas equation. So if you consider the same equation at high pressure, the thing become more complicated, and it is complicated because some other equations we need to take into account. That is actually the van der Waals equations and the particle interaction. As a result of that, the particle interaction and the finite size of the particles. I mean, the things become a bit complicated. So the equation, the equation of state for the system that is at high temperature is become achieve a new form that is actually equal to P plus A divided by small v square into V small v minus B is equal to RT. Here again the A and B are the constant that are appropriate. These are actually the constant quantity, and this the constant quantity describe that are relevant to the property of the system. So equation of state cannot be written in non-equilibrium. Again, if we want to describe the equation of state for non-equilibrium state, it cannot be written, because in that case, as I told you, we cannot exactly measure the value of P volume, and P is actually the pressure, volume and temperature. If we cannot measure the value of these three macroscopic parameter, how we can measure the properties of that? So the thing become complicated for us. So equation of states vary from system to system. This is one case, it's vary from system to system. Different system have different, because it depends upon the nature of gas, the nature of gas and all other properties. And the other thing is that the other most important thing is that equation of state cannot be written for the system in non-equilibrium state. As we discussed before, in non-equilibrium state, the properties of the systems are not constant, is continuously changing. If we define equilibrium, so equilibrium is actually the state of a system in which the property of the systems remain constant. It is not, and it is actually not changing with time. So if it is not changing with time, so this is actually the equilibrium state. But if the properties are changing with time, that is actually called as the non-equilibrium state. So if we measure some of the property in the non-equilibrium states, so it will have one value at some time, and after some time, as because the properties is not constant, after some time it will achieve another value. So if we use the first value, it will be hard for us to know the real value, because the next value will be the real value, or maybe not real. It can change after some time, but it will not be exactly the real value. So that is why we cannot exactly measure and we cannot treat the value in sort of equation. That is actually the equation of state. So for non-equilibrium states, So that is why when we are discussing any system, we are discussing the system that is actually the system that is in equilibrium. But in non-equilibrium states, so all the equation what we measure, just like the PV is equal to nRT for the ideal case equation for the at low pressure, that is actually for again for thermodynamics equilibrium system. And again this is the this equation P plus A divided by U square into V minus P is equal to RT, that is again for a system that is to be in equilibrium, but that is actually at high pressure. So anyhow, this is something about the thermodynamic equilibrium, which is the combination of the thermal equilibrium, chemical equilibrium, and mechanical equilibrium, and the equation of state, how we can define any particular thermodynamic system. So inshallah in next slides we can move forward to understand the some other relevant topics about the thermodynamics. Thank you very much.